you send it in?
All right. So, how is it going?
It's not.
What's that?
You gave out an assignment.
I gave out an assignment?
It's not good.
What is this? This is how you do it. Oh, I did the brush. That's super interesting.
Next week, yes. Because we're not having class Thursday, remember?
Told you guys.
Huh?
We don't have to do stats on Monday, right?
Yeah, this is still going to take forever.
We have no class. We don't have class this Thursday. A week from Thursday.
Oh, we're Tuesday.
Yeah, we're Tuesday today. Yes. Yes, we are.
Choose a different brush where it's not.
All right. What's that? No. Where is Chelsea and Haley and
Chelsea's dying.
Haley's definitely not sick.
Haley's definitely not sick.
Definitely
Yeah,
not sick.
she's just late, probably.
Haley's skipping.
Haley's skipping? That doesn't surprise me. That's what Haley does. Hopefully she'll.
Can we go to a different classroom so when she walks?
Or we can go outside.
Yeah.
It's a little harder to go outside. Everybody, seriously, I get that all the time. All right. So, we talked last time about least squares. What am I doing? This is a different notepad. What's that? I'm going to do some stuff on the computer. So, why is... Okay, never mind. I don't know why it's doing that. There's Haley. What? Oh, here we go.
It's supposed to deal two parts when you're determining suit, rank, and
Add a page. There we go. That's what I wanted to do. Awesome. Okay. So last time we talked about least squares. We're going to continue on with that discussion and then start going into some newer stuff with least squares so that we can talk about doing dot products in general, not just with Euclidean vectors, but you can talk about doing dot products of functions. And then we're going to talk about how we can use, not today, we'll get to it next week, but talk about how we can use basically what are called trigonometric polynomials to approximate periodic types of functions. So we'll get into what I mean by that next week. But so last time, remember when we had the least squares information? When we had the least squares information, the idea was that we had a bunch of points, x1, x2, down to xn, y1, y2, down to yn. We started it off by doing a line, but we can do whatever type of function that we want, as long as we can set up a system of linear equations in the constants that we're trying to find. So we'll talk about doing that for a couple of different types of functions today to go through the examples. So we wanted to fit these points to the model y equals basically ax plus b, or a plus bx. I can't remember which way I wrote it. It doesn't really matter. As long as you know that to keep track of where the things are for which columns. So the idea is that we want to plug in x1 into this function and get out a y value, hopefully as close to y1. Plug in x2 in to get a y value out that's close to y2, and so on down the line. Right? That's the idea. So when we set up the system of equations, you would want ax1 plus b equals y1, ax2 plus b equals y2, so on down the line, axn plus b equals yn. And what we're trying to find are the A's and the B's. So if we write this in matrix form then as an augmented matrix, notice that the coefficients on the A's are your X's. The coefficients on the B's are all 1s. The variables that we're trying to solve for are A and B, and then the right-hand side will be y1, y2, up to yn. So that's what the system of equations looks like. Notice we have typically we have a lot more points than we have coefficients that we're trying to solve for. So we get what's referred to as an overdetermined system. We have more information than we need to be able to solve for the A and B, get values for those. The risk you run with overdetermined systems is that you have too much information and you get an inconsistent system. In fact, if any one of these points falls off that line, it's going to be inconsistent. Because you know that 2 points completely determines a line, so then every other point has to be on that same line, or you're going to get an inconsistent system. Okay. So, ouch. In general, this system is going to be inconsistent. So that was why we talked about doing the least squares idea, trying to find a system or a solution to the system of equations that's as close to as possible to these values in some error sense. So the way we set that up then was this is our matrix. We call this the matrix A. We call this the little b. And we set up that normal equation that was A transpose A inverse times, or sorry, not inverse, A transpose AX is equal to A transpose B. We went through all that work last time to get to that point, where we talked about doing the projections and being orthogonal complements and all that good stuff. Right? Did all sorts of linear algebra last time. It was lots of fun. I had fun. Okay. That's all that really matters. All right. So then we said if we wanted to solve for x, we want to apply the inverse of this matrix to both sides so that we can get x all by itself. Again, this was called the normal equations for this. This, you have to make sure we have invertibility. As long as you have more points, as long as you don't have them all fall on a vertical line, this will always be invertible. You need to make sure that your original matrix has all linearly independent columns. It's the important part. Make sure you have enough linearly independent columns to be able to do it. So there we get our least squares solution by applying the inverse of A transpose A to both sides. So that gives us our least squares solution. So we can do this now for pretty much, again, any types of functions that we want, provided that we can set up a system of linear equations in the constants, in the coefficients. So just to do an example again, in GeoGebra here, let's do it this way, I guess. Or act like I want to rename it instead. That'd be great. All right, so let's just put in some points and see what happens here. I did this last time, but let's just make up some points. Let's say we had the points 5, -2. I'm just going to make up some x values, 7, 3, 1, and some y values of -2, -6, 8, 2, and 4. Whatever, it doesn't really matter. All right, so let's make a list of points here so that I can see them all on the screen. Which one's missing? The -6 one? There it is. There we go. All right, so we have those 5 points. It doesn't matter how many points there are. We're just going to type them in. I just did the X's and the Y's for each column. So I want to set up the least squares model. So again, it doesn't really matter which order you do it. If I do A plus BX or AX plus B or BX plus A or whatever, as long as you're consistent going down the columns and know where you're going to plug the coefficients in. So if we did it last time, I think I did the constant first and then the variable. This time I'll do the variable first and then the constant. Honestly, it does not matter, again, as long as you're consistent down the columns. Okay? So if we want to fit this to y equals ax plus b, then when I make up the coefficient matrix, my A, if I want my A and B to correspond to the first column and second column, notice that the A is multiplied by the x values, right? So I would have 5, -2, 7, 3, and 1 for the A column, because those are the coefficients I get when I plug those numbers in for x, right? We agree? Okay. So then for B, notice that no matter what I plug in for x, the coefficient on the B is 1. So I'll just get 1s down that column. So I'll just type that here in GeoGebra as well. So I'll just copy these values down so I don't have to retype them because I'm lazy. And then I'll put in 1s here. And we'll try this again. We'll go over and create a matrix. Now, of course, I can't see it on here because I don't have the algebra window up. There we go. Now the algebra window's up. So we had the list of points created, but what I'm interested in doing here is working with this matrix. So again, once we have the matrix set up, we're essentially done. We just have to plug it in the formula. The other piece that I need is the B vector, the vector with our y's. So where did the spreadsheet go? There, that's buried. There it is. I also need a vector with my b's. So these were the y's give me that b vector. So I'll just create a matrix with that too. So M1 is our coefficient matrix, M2 is our constants. So now we're ready to roll with this. So I can do, the formula again is the transpose, if I can spell the word transpose, the transpose of M1 times M1, right, because it's A transpose A, inverse, so I just did to the -1, and then it's multiplied by A transpose, what the heck just happened? Oh, stop! Transpose of M1, and then we want to multiply that by M2. So let's see if I can widen this a bit so you can see it all at once. So again, this is the syntax. Again, the transpose of M1, that's A transpose times A. Take the inverse. And then A transpose times the B. like I said, once we get the matrices set up, the formula is the same every single time. The only thing that's going to change from problem to problem on the least squares model stuff is what does the matrix look like? That depends on the form of the function and how many coefficients you're trying to solve for. Number of coefficients you're trying to solve for will give you the number of columns every time. Number of points gives you the number of rows. Okay. All right, so here's our answer in M3. So this is our A, this is our B, right? So this is the coefficient on my X, this is my constant. So if I want to be, well, relatively clever, I could take, let's see if this will work. I could take the row vector, which is x comma 1, and then multiply it by the M3, which is that column vector, and it didn't give me the x. Of course it didn't, because you hate me. All right. Anyway, I don't know why I didn't do that. Why do you? Yeah, okay, so it thinks there's an x there. That's interesting. All right, I'll just type in the line. So if we do 1.05x minus the 1.7, I was trying to be clever and get it to just, if I took the x comma 1 and multiply it, it should have given me 1.05x minus 1.74, and then I would have plotted it, but it didn't want to do that. So anyway, I just typed it in so that I can see what it looks like. Is it okay? Yeah, for you.
What was your M2?
The M2 is just the y values. I just highlighted the y values and said create a matrix. Is it okay? So notice that the line, it's pretty decent. I mean, it's going up and to the right, like it should. That's what the points kind of generally do, right? It's not necessarily a great fit. We're going to talk here in a minute about how we can determine some semblance of fit, if you will, to this. And again, from a linear algebra type of perspective. But maybe you wanted to try to fit it to a cubic rather than a line. So maybe instead of doing ax plus b, you wanted to do, say, y equals ax cubed plus bx squared plus cx plus d. And try to figure out what the a, b, and c, and d are. Well, in this case, then, our matrix, again, will have 4 columns. We'll have a column for each of the a, b, c, and d. And then in our A column, we'll cube all of the x's. In the B column, we'll square them all. The C column will keep them as x. And the D column will be all ones. So if I go back over to the spreadsheet here, let's move some things over here. So this was, all right, so those were my coefficients on the x's and on my b, right? Or on the a's and on the b's. So in the A column here, then I'm going to take the 5 and cube it. And in the B column, I'm going to take the 5 and square it. So just using the cell references, and the reason why I use the cell references, of course, is so that I can pull that down. So that's our coefficient matrix again. And then we can do this exactly like we did before. We highlight the matrix, or highlight the cells that we want to create the matrix, I should say. And since I moved some things around, it changed it. It automatically changed my M. Right? It changed my M1. It didn't make a new one. The reason why is I did it in the same spot I did it before. I didn't necessarily want it to do that, but that's what it did. Did everybody get to the point where they've created the matrix? Not quite? Your shift key not working again?
No, it works for like a minute after you have the compressed air.
Yeah.
But then it stopped.
Then it stopped again?
Yeah.
So you need to just get a spray, compressed air and just spray it in there every once in a while. Yeah, it is funny. Well, it's like at the gas station down the road. It has this air, and then it has the little symbols for Visa and MasterCard underneath it. All right, so my guess is, no, it didn't. It must have gotten rid of it somewhere. Okay, so this is my M1, this is my M2. I'm confused why I deleted the other one. It must have deleted it when I moved the other one. So again, our equation is the transpose. For some reason, I cannot type TRA when I want to try transpose. I always try TAN. I have no idea why. Oh, for heaven's sake. When the transpose. Well, what's annoying is on GeoGebra you hit Enter to get it to pop up, and Excel you hit Tab to get it to come up. And so I do the wrong thing in the wrong in the wrong program. Transpose of M1 times M1 inverse times the transpose of M1 times M2. So there are our coefficients. So if I take these coefficients, I'm going to try this again and see if it decides to be dumb again. Yeah, it doesn't like it. I don't know why it doesn't do it. It should be doing a product of those two matrices, but it's not doing it the way that I want to do it. Anyway, I'll just type it in then. So it was 0.19 x cubed. And then minus whatever that coefficient was, 1.48 x squared, and then plus 1.54x plus 4.4. And in that case, we're much better. Which makes sense because we used a higher degree polynomial to try to get a little more accuracy. Had I gone to fourth degree polynomial, I would have gone through all 5 points. Because 5 points determines a fourth degree polynomial. As long as they're not all on the same cubic or less. Right. So, and it makes sense what it was trying to do, right? It's still giving you that lower left to upper right, like it did with the line, but it made the bend here in the middle to catch these points that are going back down again. So it gave us a nice approximation. And again, without having to try to go through all of the points. Imagine if you had 50 points, you wouldn't necessarily want a 50-degree polynomial. And given the, why not? And given the complaints I've been hearing, I'm guessing you don't want to do 50 cubic splines either.
Do you? I feel like I did 50. I definitely feel like I probably did like 15.
15.
Are we counting all my failed attempts? Oh, that would be. Yeah, no doubt.
That's okay? All right. So let's talk a little bit about how we can judge error. So to do a little bit of the linear algebra setup, I'm not going to go through all of the details that I could go through with this, but I want to go through a little bit with the, pardon me, the interesting parts of the linear algebra that can get us these computations pretty quick for a measure of how good the fit the model is. Okay, so there is what's referred to as the sum of squares, the sum of total square error. So what we mean by this is each of the points has a distance that is away from the mean of the y values. So when we do the sum of the total squared error, that's going to be the sum from I equals 1 to n of the points minus the mean squared. If you don't square it, you'll always get 0. Anytime you do the sum of the deviations from the mean for a data set, you always get 0. That's why when you do standard deviation, you have to square things. It doesn't get it, or take absolute value, which is also harder to work with. So this gives us the total squared error. The notation for this is typically SST. So that's the SST is your total sum, the sum of the squared error, SST. So we also have what we call the sum of residual squared error. So your sum of the residual squared error is the sum from I equals 1 to n of yi minus, traditionally this is called y hat squared. What's our SSR? The y hat is really the output you get from the model. So the way I wrote this is y equals ax cubed plus bx squared and so on down the line. We're modeling this thing, so this is really your y hat. When you put inputs in, you get out a y hat. So this is how far each of your modeled values is from the data points. As long as there's a non-zero constant to your least squares model, as long as there's some sort of a non-zero constant, this SSR will always be less than or equal to, less than or equal to your SST. So the ratio of those things makes sense. So we get what's referred to as the coefficient of determination. Which we refer to as r squared. And this is equal to 1 minus the ratio of your residual sum of squares divided by your total sum of squares. So your residual squared error over your total squared error. I'm not going to go through a lot of the details. If you want to go through some of the details, Well, you can talk to me after class, but we can also do it in a stats class. But the idea is that when you're doing a model, there's certainly a total error of how far away data points are. Each data point is away from the mean. Yes.
In the sum of total squared error, what is the y bar?
It's the average, the mean. Yeah, it's the mean of the y's.
Okay.
Sorry. It's how far each data point is from its mean and then square it. So for that total sum of squares, how far away it is, it's made up of this model piece plus there's a random error piece. So the model piece, if I go back over to the picture, the model piece for, say, the line is the vertical distance between this point and here. That's our residual error, that distance, for that particular point. So that's one residual. So this would be another residual, this one would be negative, right? This one's negative, that one's positive. Okay. So those are what we mean by the residuals. And it makes sense that there should be some that are positive and some that are negative because we're trying to minimize the error, right? It wouldn't make sense for all of the points to lie above the line or all of the points to lie below the line because you could probably make the error better by shifting your line. That makes sense? Now again, like I mentioned before, your residual sum of squares is, pardon me, the residual sum of squares is always less than or equal to your total sum of squares unless your model goes through the origin, and then some things can get screwy. But in general, it's always going to be less. So this r squared value here is always going to be, well, it can't be less than 0 because we're doing squaring things and adding them up, right? So it certainly can't be, I can't make it, this part negative, and it's never going to be bigger than 1. So the smallest this could get is 0. What that would tell you is that your y hats are falling exactly, your data is all on the same line, is what that's telling you. Because that would tell you that these are predicting it perfectly. Because where your y hat is the prediction for the y sub I. Yeah, I should write that as y sub I hat. Yeah, I should have a sub on that here. In particular, I'm putting the x in there. I'm just putting the I on there so that we know that we really are doing the estimate for the ith one. So anyway, the only way that this could be 1 is if my residuals is 0, which would say that my points are all lying on the line. So they were all linear to begin with, or lying exactly on the function, whatever function we're trying to get to. Okay? And again, since the residuals is never bigger than the sum of squares, this always has to be positive. Okay. So again, the error can be broken up into two pieces. There's error that's explained by the model, and then a random error that just happens with whatever observations you're doing. There's conditions that weren't just right, so it made a random error. Anybody who's done a scientific experiment knows that anytime you go through a lab and look at, well, okay, I'm trying to verify whatever property we're doing, it never comes out exact. Mine never did in high school. Relative error, 1,400%. Yeah, it's great. It's perfect. Great. So anyway, it's never perfect. So there's a random piece that's in there as well. Okay. So what this coefficient does is it says how much of the error that's going on is explained by the model. How much of the variance in the data is explained by the model. Because SST is a measure of variance, right? How far away is each data point from the mean? That's a measure of variance, right? The variance would be 0 if every value is exactly the same. It's always equal to the average, right? The farther away things get from the mean, the higher variance there is, right? So this is variance in all of the data. This is variance in the model. So this is an explanation of how much variance there is explained by the model. And then whatever is left over, because think about it, the variance is either just the residuals or just the error. Those two things together have to add up to 1 when I divide out by the total error. Right? So this is explaining, when I subtract this over, this is explaining all but the error part. Okay? So, pardon me. This gives us a way to measure how much variance is explained by the model. So, how can we get at this from a linear algebra perspective? Because I could do this with a spreadsheet and go through and calculate it all. But again, I want to show a little bit of a trick that you can do with linear algebra stuff to actually compute this, because I think it's a little bit more fun. So let's notice some things here. So if I take, let's just do this by a 3 by 3, just for argument's sake. And I just put a bunch of 1s in here. And I multiply this by, say, x1, x2, x3 in front here. What do I get for, oops, what do I get for the answer? Yeah, it's just get x1 plus x2 plus x3 in all 3 components, right? We agree? So notice when we have this matrix of all 1s, we can get the value of the sum of the components in each of these spots. Okay? All right. Well, if instead of having 1s there, what if I had 1/3 everywhere? What would I get in each component? Is it times a 9th, or? I think it's just times a third, isn't it? Because I'll have a third x1, a third x2, a third x3, right? So if I put a third there everywhere, these just all get divided by 3. And what did I just do here? What did I get here? What did I get? What did I just compute for these 3 numbers in each component? The average, right? It's the mean, isn't it? This is the mean of each of these, right? We agree with that? Well, we can compute this pretty quickly if we do the following. Let's let, I'm going to use an I. It's not the same I that you use in physics, by the way, or in Calc 3, so don't get confused by it. I'm just going to call it I. I can't, well, if I try to write a Greek letter I, it looks like an I, just without a dot. Right? So I'm going to write it as a vector I, but what I really mean is I want the vector, column vector with all 1s. And let's just suppose that this is an n by 1 matrix. Then if I do 1 over n times I transpose times I get this matrix thing that this n by n matrix that I just did above. You can check that out because I'm doing a 1 by n. Did I just do that backwards? I need the transpose on the other side. Sorry, I need the transpose here. Doesn't really matter. I'm just doing a way to get the matrix to be formed. I need the transpose on the other one. Because I'm thinking n by 1 times a 1 by n gives me an n by n. So the way the matrices work for multiplication, right? And all we're doing is just entry times entry all the way across. All right. So why did I do that? Well, I just said, notice that you get the average when we do the other thing, right? So one of the things that we want to compute, especially for the sum of the total sum of squares, that SST, I need to calculate deviations of the deviations from the mean for each data value, right? So one thing that I want to notice is that if I have a system y, so I'll say, let's just do x because I've already been using x's. Let's say I want to do x1 and subtract the mean. So that would be x1 plus x2 plus x3 over 3. Well, notice that if I rearrange this, I get 1 minus a third times x1, and then minus a third x2 minus a third x3, right? We agree with that? Okay. If I did the same thing for x2, I would get negative 1/3 x1, and then plus 1 minus a third x2, and there's a reason why I'm leaving it like that, and then minus a third x3, right? And then likewise, if I did the last one, I would just shift that 1 minus 1/3 over to the other one. Do you agree with that? Okay, so let's go back up to this multiplication that we did here, right? When we did this multiplication, we took the 1/3, the 1/3, the 1/3, and multiplied it by each of these, right? And added them together. And then likewise down the rows, right? Okay. But when I do the deviations, I want to change what's on the, basically what's on the diagonal, right? If I want the deviation from x1, then I want to, or the deviation that x1 is from the mean, then I want a 1 minus 1/3 on the diagonal, not a 1/3, right? If I want the deviation from x2, I want a 1 minus 1/3 on the diagonal for x2, and not on the x1 and the x3. So in particular, if I want deviations, then I want, along the diagonal here, I want to change these numbers. I want to do 1 minus that. And I want to leave the rest of, well, I want to make the rest of them negatives, but I want to leave the rest of them alone, essentially. Well, what matrix do you know has, so one's down the diagonal and would leave the rest of them alone? The identity matrix, right? So if we do the identity matrix minus this 1 over n times I transpose, that would give us a matrix that looks like 1 minus 1 over n, 1 minus 1 over n, all the way down to 1 minus 1 over n, and negative 1 over n's everywhere else. And that would be exactly the setup that we would want to be able to compute deviations now. Okay? So let's give this matrix a name. Let's call it n, because I said so. it relates back to the normal equation stuff, so that's why we're using that. So then when I take the n, so let's say if, oops, I'll call it the y vector is our y1, y2, out to yn. If those are our actual observed y values, then ny is an n by 1 matrix that has the deviations from the mean. The deviations from each or of each data point from the mean. Just by the way it was computed. So notice that I can calculate the deviations just by doing matrix multiplication. And I can create this matrix pretty quickly. So I just needed vectors of ones and then just multiply them together and I'm on the way. So I can do this pretty quickly. Of course, if you've done things as statistical packages, you're all thinking, I could do it really quickly just by putting the data in and calling it good. But, okay. But I want to do this. So anyway, all right. So let's talk. This is just the deviation. Remember, we have to do the sum of the squares of the deviations to get SST, right? Right? Okay. So to do that, let's notice something about our n matrix. In particular, let's take its transpose. For people who are in linear and have done transposes, what does the transpose do with respect to the sum? Distributes, right? So we would have, oops, I transpose minus 1 over n I transpose. Now some other properties. Well, what matrix is I? Identity matrix. If you take the transpose of the identity, what do you get? The identity back again, right? So we get I out, right? And then what can I do with a constant inside the transpose? I can pull it out. And then when you do the transpose of a product of matrices, what do you do? Yeah, you reverse it, right? You take the transpose of each, but you reverse it. It's kind of like what you do with inverses. So this would be I transpose, I transpose. Right? You reverse the order and take the transpose of each piece. But what do you get when you take the transpose of a transpose? The original, right? So this is just I minus 1 over n, I transpose, and that's where we started, isn't it? So notice that n, this matrix n that we have is symmetric, which we could have seen just from how we wrote it out up here. It definitely is its own transpose, right? But I wanted to play around with the algebra. That's fun. All right. What if we took n and squared it? Took n times itself. Oops. There's a reason why I'm doing this. More than that I like algebra. Remember, we have to be careful when we FOIL with matrices because the order of multiplication matters. Right? So just to be cognizant of that. But when I do the first ones, I have I times I, which will give me I. I'd have outer would give me I minus 1 over n times I transpose, but that's just going to be 1 over n I transpose, right? Because it's just the identity matrix times that one. And then, likewise, we get the same thing here. The reason is that this is the identity matrix, right? This would be the reverse product, wouldn't it? And then the last one would be plus 1 over n squared times this matrix squared. So, we have here, we would have I minus 1 over n I transpose minus 1 over n I transpose plus 1 over n squared I transpose squared. Whole thing squared. And rather than going through a nice long-winded argument for what that is equal to, let's just think about it. Remember, I transpose was the matrix that gave us all ones, right? Right? So if you've got a bunch of, let's just think about it. If you've got a bunch of ones, and I multiply it by itself, let's just multiply it by one of these vectors because that's all I really need. When I take all of these ones and multiply them by all of those ones, what am I going to end up with? If this is n by n to start with, if I take all of these ones and multiply by all those ones, what am I going to get? I'm going to get n, right? Because I'm going to add n ones together. And that's what's going to be in every single product, right? So that when I take that and square it, I'm going to get just a matrix that's full of n's. What's out in front of that matrix full of n's? 1 over n squared, right? So I can take one of those n's and cancel it with that matrix of n's and make it all ones again, right? So this matrix right here is just 1 over n times I transpose. When I do that matrix and square it, I get a bunch of n's. I take 1 over n, one of the 1 over n's back through it again. It makes them all ones again. Okay. So notice now we've got 2 minus 1 over n I transposes, but plus another one. So this becomes I minus 1 over n I transpose. Oh, look, look, look. We're back to where we started. So this matrix is symmetric. That was what we're showing it as its own transpose. It's also referred to as idempotent. It's when you square it, you get back to itself. That's what idempotent means. Now, why do I care? This matrix, did I call it Y before? Yeah. This matrix, again, was the sum of the deviations, correct? That gave me one of I'm sorry, it was not the sum of the deviations. It gives me a vector that's full of the deviations, right? If I do this one, do transpose on the other side, instead of getting a column vector that's full of the deviations, let's do it this way. Sorry, let me do it this way. Let me erase this. Let me write it this way. The ny gives you a row vector that is a column that's full of the deviations. What I just wrote, ny transpose, is going to give you, instead of a column vector, it'll give you a row vector, right? So when I take the row vector times the column vector, if multiplying this way, I would get a 1 by 1 matrix. That would be the sum of the squares of the deviations. So when we do, if I do, so this one is a column vector with the deviations. This is a row vector with the deviations. Oops. So if you do ny transpose times ny, this will give you a 1 by 1 matrix that is the sum of the deviations from the mean. That's SST. That literally gives you the SST value. Now, one of the reasons why I went through the other stuff is because I can simplify the left-hand side. Greta said a minute ago, what do you do with the transpose? With respect to a product?
Take the transpose of both and flip them.
Yep, take the transpose of both and flip them. And what did we just say? What's true about n transpose? What is it the same thing as? N. And what did we just say that n squared is the same thing as? N. So I can simplify that. So this piece right here is your SST. So it gives you a way to calculate your total sum of squares using matrix multiplication. So let's do that for the one we have over here. All right. So this is our y, right? So we've already got that created as a matrix, don't we? It's M2. Okay. So the other thing that we need to create is our n matrix. So in this particular case, I think it's probably just as easy to type it in because I need, how many data points do we have? 5? Right? So I could just do 1/5 in each of these. So I'll just copy that across and copy that down. And then I'll create that matrix. And it has it as M5. I'm reading that right? Yeah, point.
Why don't you have to do the one line?
Oh, I'm going to.
Oh.
Yeah. There's a command in GeoGebra that has an identity matrix built in. That's why I just did that this way. Okay. So, yeah, for the one, so we have the y put in there already. That was M2, yes? Our y was M2. So I'm going to do the transpose of M2. I'm going to multiply it by, but parentheses. Notice I started typing the word identity. Command comes up. So that is, let me shrink this over here. So it says identity of number. So I just put a 5 in there so it tells it the dimensions. Okay. And then minus M5 is the matrix we just created. Right? So this is y transpose times n. And then I need to multiply that by y, which was M2 again. And it gave us a 1 by 1 matrix like it's supposed to. So the sum of your squares of all the deviations from the mean is 116.8. That's the SST.
So this maybe sounds silly, but like, what do you mean, like I know what the mean is, the average, but like looking at, because like the y hat one, like where you're comparing the one value to the other one. So when you say the deviation from like the mean, like maybe just.
So let's just see if I can do the mean here real quick. All right. So the mean is 6. So if I just plot, oops. Okay, y equals 6. There we go. All right, so really the mean's 6. I don't believe that it's 6. Oh, thank you. It is 6/5. Thank you. You're all about the ticks, I tell you.
Was it?
Yeah.
There. Better? All right. Hey, at least I knew something was wrong. I don't think it should be a tick. I knew it was wrong. All right. So when we're doing the sum of the total error, the SST, the total sum of squared deviations, that's the distance would be this value down to the mean. And we're squaring those. So
Okay.
it'd be those differences graphically.
Okay, so then what?
So that's okay. Go ahead. What were you going to ask?
I was just gonna say, like, what would the benefit of using this? Like, the benefit of using this, finding this error with using that.
So the error using that is the variability period. That's how the variance is defined. I have to divide by something, but that's how the variance is defined. Because what we're interested in is if we've got these data points, how far away are they from the true value? A lot of it's involved in doing sampling from a statistical perspective. So if you have a sample of things and want to try to estimate the mean of the population, the mean of everything from just taking a few things, then you want to know how much variability there's possible in your data and then how close it would be. And it's used to estimate those kinds of things. I didn't explain it very well, but that's the whole point of doing these particular things. So, but if I try to just use the absolute or the actual signed differences from the mean, you'll always get 0. So I can't just add up the errors from the mean, because every time you do that, you always get 0. Anytime that you take data point minus mean and sum it up, you will always get 0, no matter what. Okay. So I can't just add up the deviations. Now you could do absolute value, but a lot of the stuff that you do with trying to analyze these things, you try to do from a calculus perspective. And absolute value isn't a very easy thing to analyze from a calculus perspective because of having sharp corners in it. So instead of doing absolute value, you square it instead. Still makes everything positive, but it does so smoothly so that you can do more calculus types of things with it. Yeah, Grace.
Where did this 6/5 come from?
I added up all the y values and then divided by 5. I took the average. First, I only added them up. Haley told me to divide by 5.
That's what she
And
said.
that's why you got.
Is that what you just said? That's how we got the 6/5. I was doing an average and forgot to divide by how many there were. Hey, at least Haley was paying attention.
For once, yeah.
For once. All right. Does that help a little bit, Morgan?
Yeah.
Because you probably haven't had much with statistics at all.
No.
Yeah. So
So then, like, where are 6 come from again?
the 6 is just adding up the y values. I was just doing the
Oh.
average of the y values. That's where the 6 came from.
Okay.
And again, if you just kind of look at it graphically, remember that when you go difference from point to mean, and do those distances, that certainly looks bigger than if I go from point to line. Right? So the whole point of this, again, when you're doing the model is trying to explain variability in your data points. Right? But it can't catch it all because you've got random error that pops up when you do sampling kinds of ideas. So I can't catch all of the error, but it catches some. So the R squared value that we still haven't gotten to yet, the R squared value gives you a way to measure how good it is. Okay? All right, so let's see if we can figure out how we can get to the SSR part. Oops. So when we do the SSR part, let's see if I remember how to do this. I mean, I can do it just with a spreadsheet. So remember your y hats. Right on here. So if I just do it for a linear model, your y hat again is your ax plus b, that model. And what we want to compute is the difference between the yi and I'll say y sub I hat, that sum. And squared, which means we want to do the sum of the y sub I minus, this would be axi minus b, and square it. All right, so these should be deviations again, right? And we want to square the deviations. So our goal here would be to try to find, let's see, this is what's looking like what we had before, except that we had y bar here, right? Do you agree? This looks a lot like what we had before, except we had y bar rather than y hat. So if I want to do these deviations, I want to try to figure out a way to get to this point, right? To figure out how to do this. So let's see. Where did this ax? How do we get our y hats? Well, again, that would be our coefficient matrix times the data points that we have, the x's, right? Because each of those would give our what am I trying to say? Our outputs. So when we had our coefficient matrix, what was our coefficient matrix? The trying to think of it this way. We know that the solution are the values for the A and the B. Remember, the values for the A and the B are given to us by what? If we had A and B, remember that was our A transpose A inverse times A transpose times B, right? That was our solution, wasn't it? Okay. So if I want to figure out a way to do this in a similar fashion that we did before, let's see. This is that's how we get our A and our B. And I want to calculate what you get when you put in the xi and the b, or the xi and the, each xi in there. So what do I need to do here? Yes?
Could we like take the one with the x's and the y, and then multiply it by the AB, and then get the y's, and that's what we want to do.
Okay, good. Okay, so I want to multiply this by the a and the b, so the answer that we got, right? Is that what you're saying? If I take this by our, what was it, the x1, the x2, the xn, and the 1s, and multiply that by the AB, that would get us our y hats, exactly. This would be our matrix of y hats. That's exactly right. So this would give you your y1 hat, y2 hat, down to yn hat. Good. All right. All right. So remember we used that matrix N to help us get to the deviations. If we did that again, say we had, let's just do a specific one here and make sure that we're on the right track. If we did, say we did just with the thirds again. And multiply this by, just say we had y1 hat, y2 hat, y3 hat. So give me the y values, I don't think. Let's see. So this gives me what? Let's just say we had from the first one here. Oops. May need to finish this next time. Should be okay. We already got through SST. I just need to get you through SSR to figure out the R squared. So that would give us this. I need to see if this is the deviation that I want, then I'm good. Because then I can just multiply it on the left-hand side like we did before and get the sum of the squares, which is what I want. So does this really give me the deviations from, am I doing that right? Or do I want the deviations from the, well, we want to try to get it from the deviations from each one and then add them together. So let me do this next time because I think I'm messing something up. But I don't want to mess it up anymore. Yeah, you can give me a tick. That's okay. There's more along the lines of I'm messing something up somewhere along the line here and I need to figure out where it is. What's that? That's fine. Give me a tick. That's fine. Like I said, we just need to be able to do your homework for the R squared. You'll just need to do, we just need to finish this off next time, which we can get done on Tuesday. That's not a big deal. We'll finish that off.
So no
You should be able to get everything else done on the homework besides that. Yeah, everything else on the homework should be doable. Yeah, from what we learned. What we're doing right now is just to get that find the R squared value. Literally all we're doing. Correct? All right. So like I said, let me stop here, especially since we're out of time anyway, and I'm pretty sure I'm messing something up. So we'll get that done next week.
Dr. Joe, I forgot to tell you, yesterday I went to log into my GeoGebra and it said I was banned.
It's your band?
Yeah, it said this user is banned, I can't log into my account. So I had to make a new one.
Why? That's just ridiculous.
I like how it used the word banned.
What did you do?
I don't know. Julia said it was probably because I wrote all those bad stuff about lines on the board.
Guys, that's what it was. That's just weird.
What should I call this in, like, when I'm saving the file?
What do you mean?
Like what we just did on GeoGebra?
I don't know. Don't call it what Sydney did. She got banned.
Well, let's do, like, topic.
Oh, least squares is what we're doing.
That's what I thought.
Yeah. I don't know. Don't call it what Sydney did though.
Yeah, I don't know.
Like-
I think I have a picture of it too. Because I sent it to Julia.
That's weird.